Okay, good morning. Good morning. Let's try this again. Okay, good morning. Good. All right, so today we're going to finish up chapter 7. We'll look at section 7.8. We're going to look at these things called improper integrals. So as the name implies, something is not quite right with these integrals. So first of all, we know what to do with this thing. Right, we know we can integrate that and then just evaluate the integral of f at the end points. And we could also interpret this as an area under the curve. Right, so that's a pretty regular integral. Provided that we could integrate this function, we can find out the area pretty easily. We'll look at two types of improper integrals. The first one, we'll call it type 1. It's an integral that has infinity or minus infinity as an integration limit. Or possibly both integration limits. So for example, this is a very typical improper integral. The lower limit is fine, it's a 1, nothing wrong with that. The upper limit is an infinity. So that makes this integral an improper integral. Let's first interpret what this means in terms of area. So 1 over x squared looks like this. Right? It's got a vertical asymptote at 0, and then has a horizontal asymptote at y equal to 0 to the right. This is 1. So what we're asking here, one way to interpret that is the area under this curve starting at 1 and ending at infinity. And beyond. Right? So that's what we're asking for. What is this area under the curve from here to here? Now, the fundamental theorem of calculus that we use to evaluate these things only applies to the cases where the integration limits are numbers. Infinity is not a number. We can't do this directly. So what we're going to do here is to step back from infinity for a little bit and say we're going to cut it off at a certain place. Say right here, we'll call this number A. So we'll say we're going to integrate from 1 to A of this function. And a is a number here. We can deal with that number by using the fundamental theorem of calculus. But we've got to remember that a is not the end, it's not a goal. So what we're going to do next is then take the limit and let a go to infinity. So this is how we sidestep the problem that infinity is not a number, and therefore we're not allowed to integrate with an infinity directly. Okay, let's see what we get. We're just integrating x to the minus 2, so that's pretty easy to do. And we get negative x to the minus 1 evaluated between 1 and a. Put it back into the fraction form, negative 1 over x. And all this time, just remember that a is a number, treat it like a number, evaluate this thing the regular way, and then worry about this at the very, very end. So what do we get? We get negative 1 over a minus 1 over 1, so plus 1. And as a becomes very large, 1 over a becomes very small. Eventually, that's going to become roughly 0, or practically 0. So we end up getting a 1, right? So that's the answer here. We got a finite number out of it, even though we're taking the area under a curve to an infinitely long base. When this happens, we say that the integral is convergent. Or you could say the integral converges. This is a term that we will see again later when we deal with series. Convergent, and the opposite case is called divergent. Okay, so let's think about area again. One, and then we keep going. So this number 1, what does that mean? What does it mean when I get a number 1 here in terms of area? Is it exactly equal to 1? That's right. It doesn't mean that the area is exactly equal to 1. What this means, like she said, the closer and closer we move to infinity, or the farther we move to the right, the area gets closer to 1. We'll never be able to achieve exactly equal to 1 as the area under the curve. But the more we move to the right, the closer and closer it gets to 1. Eventually, practically, it's equal to 1, but we will never get exactly equal to 1. Okay, so this equal sign here has a slightly different meaning if you think about it. When we say something something is equal to 1, usually we mean that's exactly equal to 1. But in this case, when you look at this equation here, this equal sign has a slightly different meaning. It's more of a almost equal to kind of thing. Eventually close to, but not exactly equal. And we had the same kind of issue when you first learned about limits of functions. We write limit of something is equal to a number, but that doesn't mean that it's exactly equal to that number in general. Okay, let's look at another case here. Let's put the lower limit at minus infinity this time. We have improper integral again, so I've got to worry about that. And you deal with this exactly the same way we did in the last one. We'll say it starts at a number a instead of at infinity, minus infinity. And we deal with this integral, and then we take a limit. You could also do this. I could put a lower limit as minus a and let a go to infinity, or put it as a and let a go to negative infinity. They mean exactly the same thing, so whichever one you prefer to deal with is fine. Okay, now what's the integral of 1 over 2 minus 8x? Negative 8. 1 over 8, yep. Negative 1 over 8, and, right, natural log of 2 minus 8x. All right, so you get this by making a substitution, letting u be 2 minus 8x. And the minus 1 over 8 shows up in du. Okay, then we keep going. 0 goes in. We get negative 1 over 8, natural log of 2, and then minus 1 over 8 plus 1 over 8, natural log of 2 minus 8a. All right, now think about what this is going to give us. When a becomes negative, gets closer to a very large negative number, this stuff inside here is a very large positive number. Yep. And what's natural log of a very, very large number? What's natural log of infinity? I hear 0, I hear infinity, negative infinity, what does natural log look like? Yeah. Okay. Tell me more. Where does it start? Sideways exponential. Excellent. So something like that? Good. So there's my natural log. Right? So as you see, he stated perfectly. It grows very slowly, but it does continue growing. When x becomes awfully big, natural log of an awfully big number is another big number. So this goes to infinity. So we get negative 1 over 8, natural log of 2, and that's a constant, and this goes to infinity. If we interpret this in terms of area, this means that the area under this curve is infinite. It gets bigger and bigger and bigger the more we move to minus infinity. Looks something like that. Right, the shape of this is almost the same as the last example, but in this case here, this goes to infinity. So we say that the integral is divergent, or that the integral diverges. When you say it's divergent, that implies there's no sum. The sum is either infinity or minus infinity. It's somehow not a number. When you say it's convergent, then you get a number out of it, 1, 2, pi, whatever. All right, so you can see just a slight modification of the function, we can get all kinds of different results out, a number or infinity. Yeah? 0? What do you mean? Oh, if I get a 0, then that's convergent. That's a number. Divergent is when the result is not a number. Infinity or minus infinity. That's the only cases when we say it's divergent. Any other number, the integral converges, including 0. Other questions about those two examples? Yeah. Oh, okay. I see what you mean. You could write it's equal to infinity. But the important thing is to notice that it is divergent. So you could write infinity if you want to. There's another hand up here in this area. Who did? Oh, okay, good. Okay, now let's look at this case here. We're going to move both integration limits to infinity and minus infinity. You know how to do one. Now we're going to try this with both. Double infinity here. Integral from minus infinity to positive infinity, 1 over 1 plus x squared. Here's what this thing kind of looks like. Interpret that in terms of area again. We're looking for that shaded region, the area under the curve. And this time we're going to take the left tail and right tail to as far left and as far right as we can and more, and see what we get out of it. To use what we did last time, we're going to consider this as two integrals. The first one goes from minus infinity to 0, and then the second one picks it up from 0 to infinity. Now, if you are looking at this and you look at this again, we could also take advantage of symmetry and just calculate one of these and multiply by 2. Right? That's one option that we can have. But we can leave it like this too. This is perfectly okay. Okay, now we deal with this first integral the way we dealt with the second example we did. We let a go to minus infinity and integrate from a to 0. And then we're going to integrate from 0 to b and also let b go to 0. Now, what is the integral of 1 over 1 plus? Actually, take 1 minute and work out the integral of 1 over 1 plus x squared. You should be able to do that. 1 minute. Okay, that's 1 minute. What's the answer to, what's the integral of 1 over 1 plus x squared? Wow, let's see. Let's hand up if you know it. No, not quite. It's a trick of some sort. You're on the right track. The what? Inverse tangent. Yes. How did you get it? Okay, you recognize the integral. Good. How else could you get it if you didn't know that? Yeah, exactly. Yeah. So what you could do is to look at this as this thing, and then do a trig substitution. Right, so the square root term is 1 plus x squared, so that goes here. Constant goes down, this goes here, and so on. Right? So that would get you the inverse tangent as the integral of 1 over 1 plus x squared. Okay, then we get inverse tangent of x a to 0 plus limit b to infinity inverse tangent of 0 to b. And then we continue. So we get inverse tangent of 0 minus inverse tangent of a plus limit b to infinity inverse tangent of b minus the inverse tangent of 0. Okay? Okay, to evaluate these things, it helps if you know the graph of inverse tangent. And we'll start with tangent. You know how to get the inverse. So here's tangent. Right? It has two vertical asymptotes in the region that we're looking at here. And you remember how to get the graph of the inverse function if you have the original one? You do a reflection about the line y is equal to x, right? So what happens then, the vertical asymptotes turn into horizontal asymptotes. Pi over 2 minus pi over 2. And this gets reflected across the line y is equal to x. Something like that. So this is our inverse tangent graph. Okay, then we'll pick it up with the limits. Limit a to minus infinity, inverse tangent of, I'm just rewriting that right now. Okay, then you look at the graph we got here. Inverse tangent of 0 is 0, right? So that's a 0. Now, inverse tangent of a, when a goes to minus infinity, we get minus pi over 2, right? When you follow this to minus infinity, we get minus over 2, pi over 2. This, when b becomes large, you follow this one, and you get pi over 2. And this is a 0, of course. So what do we end up getting? Pi over 2, pi. I am. That's why this turns into positive. See, minus pi over 2. So positive pi over 2, positive pi over 2. I guess I'll put a sign here, there. Okay, in other words, telling us that we get this thing, we get this result here. Now, the first time I saw this result, this completely blew my mind. Because you look at this function here, 1 over 1 plus x squared. There's no trick whatsoever in there just by looking at it. However, when you integrate from left to right all the way through, you end up getting exactly equal to pi. Now, pi has absolutely no business getting in here, but yet it is. That is the, to me, this is amazing. Why is pi here? In other words, you can define pi using this way. The typical way we define pi is the ratio between the circumference and diameter of a circle, right? That's the most typical way to define pi. However, if someone asks you, what is pi, you can tell him this answer, and you will still be right. It's an integral from minus infinity to infinity of 1 over 1 plus x squared. Again, pi has no business to being here, but yet it is. This is kind of an amazing result. What mathematics is telling us, sometimes, it just blows my mind. You can also define the number e in an equally strange way with integrals and series, all kinds of things. And many of these integral results are things like that. You look at it, when pi or e have absolutely no business getting in there, somehow ended up in there. Okay, anyway, type 2. So we look at type 1. Type 1 was simple. When one of the integration limits or both go to infinity. Now we'll look at type 2. And type 2 is when f of x, the function you're integrating, is discontinuous somewhere between a and b. It may happen more than once, but if it happens at least once, then we have what's called a type 2 improper integral. For example, (1 over x squared), and we're integrating from -1 to +2. Interpreted in terms of area, we get this kind of shape, -1 to 2. But notice that 1 over x squared becomes discontinuous at 0. Right? And we handle this exactly the same way we handled infinity. We cannot cross this vertical asymptote, but we can stop at some point right before it and then get closer and closer each time. So first we break this up into this thing. Zero is that line we can't cross. And of course, we can't integrate to 0 because we got a discontinuity here. That function doesn't exist at 0. So we do this. We take that 0 out, change it to some constant called that a, and we let a go to 0 from the left side, right? We're coming from the left side here. We allow a to get to 0. The other one, same idea here. We can't start at 0, but we can start at b, some finite number b close to 0, and we make it even closer to 0. And then integrate that. We integrated this in the first example we did today. And then we integrate this, evaluate that the usual way. Limit a to 0 from the left side, negative 1 over a plus 1 and then limit b to 0 from the right side, negative 1 over 2 plus 1 over b. Yeah.
Shouldn't the first part of the limit a be minus?
Minus, you're right, sorry, it is. Yeah, absolutely. And then the second one, we're good, right? Second one, we're good. 3 minuses, absolutely. Thanks. And now when a goes to 0, becomes very small. This goes to 0, of course. That also goes to 0. And we have 2 constants that remain. So we get minus 1 and minus 1 over 2. So what is it? Minus 3 over 2? Yeah. Actually, you're right. Yeah, yeah. You're oh, let me throw this page away. You are absolutely right. Okay, where was that? Here. Minus 1. Yep. B to 0 from the right. Minus 1 over 2. And minus 1 over b. No, plus 1 over b. There we go. Much better. I'm sorry? Did I do something wrong again? We're good? Okay, good. All right, so this, as he pointed out perfectly, this actually goes when a is a small negative number. This is infinity, right? This blows up. This is saying that a is minus 0.000001. 1 over that is a negative large number, and then negative again. That makes that a positive infinity. What about that? What do we get out of that? B is a very small but positive number. So that's a positive big number, right? Positive infinity. Question there? You okay? So the end result here is we have 1 infinity, 2 infinities, and a bunch of little numbers. This is an infinity anyway. Okay? So what is this saying? This is saying that integral diverges. If you interpret that in terms of area, we kind of expected that. You look at the area here, the closer we get to y-axis, the bigger the area underneath is. It's pretty big. Same thing here. Be very careful with this kind of integral. If we look at what we started with, if we didn't realize this is improper, and we just integrated it where we normally would, like that, and we get negative 1 over 2 plus, no, minus 1. And we get that, right? And this is obviously wrong. This can't be right. You can't integrate something that doesn't exist. And this thing does not exist at 0. So this, you get a nice number out of it, but this is wrong. Okay, so it's very important to, especially for type 1, it's very easy to recognize. Infinity in one of the bounds. Type 2, you have to be very careful. Look at the function here, and you got to find out, does it become discontinuous at some point? If it does, you got to chop it up. You can't cross that line, but you can get close to it. So be very careful with type 2. Let's look at a different type 2. Sometimes they converge. Zero to 1, 1 over radical x. And right away, we recognize that this is improper because 1 over radical x is discontinuous at x is equal to 0. And that's where we start. We can't start at somewhere where the function doesn't exist. So that makes that an improper integral. All right, so same trick. We'll start at a, and we let a get closer and closer to 0 from the right side. And because a is a number now we can deal with it. That's a number where this thing is defined. We can apply the fundamental theorem of calculus safely and directly. What do we get? We get 2x to the 1/2. And we get 2 times 1 minus 2 radical a and when a becomes small, a small positive number. This is very small positive number, eventually roughly 0, and therefore we get a 2 out of it. And 1 over radical x also has a shape. This thing has a shape that looks just like the right-hand side of this graph. Starts high and ends up low. But this thing is divergent, while this thing is convergent. And the only thing different here, if you look at just the right-hand side alone, is the power of x downstairs. And at some point, there's a dividing line where when the integral goes from convergent to divergent. Let's find out where that breaking point is. Let's integrate from 0 to 1, 1 over xp, x to the power of p. Let's find all the possible values of p such that the integral converges. And we'll follow exactly the same first few steps as in the last example. Get rid of 0, putting an a, and that a go to 0. And this is x to the minus p. Now we know the function is always defined as long as we're not exactly at 0. So fundamental theorem of calculus applies. And I'm going to rewrite this a little bit. That's a negative. So for x to the minus p plus 1, I'm writing it as x to the, no, that's not right. Now, 1 minus p is all I need. What am I doing? There, perfect. Okay? Now think about what p has to be so that x to the 1 minus p does not blow up to infinity. Well, actually, let's put a in here, and then we'll worry about that. So first we get 1, right? And when x is 1, 1 to any power is 1. Not a big deal. Minus x becomes a. Now, a is going to be a very, very small positive number. How do you